For a building to perform better during an earthquake, the plan of the building should be of very simple shape. What is simple shape? A simple shape is, for example, the building can be square, or maybe a rectangle, or maybe an octagonal, or maybe circular, or all these shapes. These shapes are called simple shapes. For throughout the height of the building, if you maintain that same plan, it is called regular building and also simple plan building. These buildings are supposed to perform better. At the same time, suppose if the building, one of the dimension of the building, either in the plan or in the elevation, is larger than the other dimensions, that is also not okay. Even though it looks regular, but it is too long or too high or too wide, that is also a problem. So there should be a phenomena which explains the size of the building and something called factor, shape factor. So it should be well within that limit. If that is there, the performance is going to be very well fine. But at the same time, even though the plus shape building or this semicircular building or this T-shaped building are also looks like regular, they are not regular. They are not, because I will explain why. But this is the second level of the thing. So one of the way that we can to come out is, suppose if I have two rectangles which is likely to form a shape of L, and if I have a separation in between these two buildings, that again becomes simple design, simple plan. That means this is one small rectangle, that is another rectangle with a clear gap. So this is going to perform much better than a building which looks like a plus or like a curve or like a T, because there is something called reentrant corner. That means if this is going to vibrate in one direction, this is going to vibrate in another direction, because lateral is two different lateral, x lateral or y lateral as the case may be. At the joint, we have this something called joint issues. So that is, we normally term that as re-entrant corner. That means the force is generated two times depending upon the sizes of these things, the size of the flaps that are projected from center. So even though, for example, you may need a structure like this, you may need a structure like this, because of various reasons. For example, one wing can be a if it is hostel, suppose this may be one wing, may be an hostel, another wing may be mess, another wing like that. There may be some different possibilities that exist in a T building or in a U building or in a plus shape, L shape, I shape, all that. These are all maybe required necessity in any structural system. But at the same time, we should understand that, let us take T for example. This portion is going to move in one way, which is, let me say, in this direction, whereas this other rectangle is going to move like this different direction. So this during an earthquake, because everything is lateral, at the joint we have something called reentrant corner, and that is the source of failure. There are two possibilities. One is you separate them structurally but connect them constructively. So that is a possibility. Still we can have a T shape. That is one solution. Or suppose you are not, that is not possible, you may have to do some different ideas here, because we know this is a section of vulnerability which need to be catered as a special case to design this as a special case. That is the way it is to be understood, the shapes. Now let us come and understand a simple concept of plan elevation issue. That is, suppose there is a tree and there is a swing, and in that swing this girl is sitting on one side. Okay, essentially it is nothing but that is unequal mass. If the girl is sitting at the center, it is regular, no issue, she can swing nicely. But if the girl is sitting on one end, that is a issue. So that means there is, in addition to lateral motion, there is a twist that happens. There is a twist that happens. So this is going to twist and then create more trouble than normal. So same way, suppose I have a structure and there is a ground shaking, and we have something called light side of the building and we have something called heavy side of the building. When I say heavy, the mass of that portion is heavier than the other portion. So I will explain later. So this is what is called unequal mass distribution. Unequal mass distribution. For example, in this we have a water tank here or some kind of heavy load here, and the normal structure on the other side. Obviously, because of the heavy weight, the motion in the heavy weight area is less compared to the free area where it is likely to move further. So this uneven distribution of displacements in the building is going to disturb the building, and it may fail because of the uneven distribution. Of course, the code says how much it can go like that. so that we can check. But these are all the issues that we have to take at the plan elevation stage itself. Suppose you take this building. You take this building, there is a ground floor car parking. Let me say it is a car parking, whatever. So that is an open area, whereas all other places are having walls. So this is also uneven distribution of mass, you can say that, as well as stiffness, because here the stiffness is different. So here also there is a possibility of lateral motion along with the twist. That is a possibility that we have to take care. Same, this is an example of a Bhuj where a building is a salt factory where they stored salt in this region, that this salt is made this side and then stored here as a storehouse. Because of the heavy mass here, the building failed very miserably here, as you can see here. Initiation would have started here. Because the rest of the place there is no mass, that kind of mass, obviously this not come down. Okay, even the failure do exist everywhere, does not come down. So this is a typical case of failures where uneven mass distribution in a building can take into failure. Similarly, suppose the same swing is made at two different levels. This is another issue. The girl may be sitting at the center, but the interesting point is one of the string is having less length than the other. Same way, suppose you are constructing a building in slope, all the columns may not be equal. This is the similar case of this. This is also equally an unsymmetrical building, equally a non-regular building, where in addition to lateral motion, there is a possibility of twist here because of the high length of the column. So this also we have to take care nicely. This obviously shows that, for example, there are columns here and there is only wall here like that. So this is a situation which brings stiffness and stiffness distribution wrongly. So there is possibility of mass distribution as well as stiffness distribution. The stiffness distribution happens because there is a heavy wall on one side and there are only columns this side. So when I say stiffness, it is about lateral deformation capacity of a structural system at that point. So when I say few columns, for example, a column can deform 12 by L cube kind of thing. So a wall may be slightly different. A wall can deform less only. So there is a less deformation system on one side, large deformation system on the other side, which is called unequal stiffness. So this also can create lateral motion as well as twist. This explains slightly better. For example, if I have a regular building, which is, let me say, 4 stories building, and you have a fixed at the bottom, if during an earthquake the building is going to deform uniformly, let me say it is uniformly because all the columns, there are 4 columns here and 4 columns here, everywhere there are only 4 columns in this structural system. So that means if the stiffness is nothing but 4 into 12 by L cube, that means that is the stiffness of each floor. So that means the stiffness distribution along the height is same. So that means the deformation also is uniformly varying. That is what is for a regular building. Suppose suddenly for some reason you remove two bays in the second and third and fourth floor. Suppose you do that. What really happens is the stiffness distribution is slightly different. For example, the lateral deformation is resisted by 4 columns here in the ground floor, 4 columns in the first floor, and only 2 columns in the um, third floor, and only 2 columns in the third. That means this is a most vulnerable thing which is likely to experience large deformation, which the building may not be able to survive that. So essentially, if you have, this is what is called setback. This is setback resistance irregularity. That means along the elevation, if you are removing certain columns for your own purpose, there is nothing wrong in that. Functional issues may be there, but unless we take care of this, that means essentially what is the solution here? The solution here is, suppose this has a stiffness of 4 into 12 by L cube, and this second floor, first floor also same thing. But go to the third floor, it is only 2 into 12. That means 50% of the stiffness is gone. So that is the problem. So suppose we are able to make this 2 into 12 by L cube into more or less equal to 4 into 12 by increasing the I value or whatever. So for example, if I am able to increase the stiffness in these columns by changing the size of the column, that means to have larger moment of inertia, maybe still it is really solved, for example. I am not saying that is solution. I am trying to convince what are all the issues in understanding a behavior of a building during an earthquake, so that you can design much better. So this is an issue. This is an issue. So this is also called vertical irregularity, wherein it is also called setback resistance. So next topic is pounding. For example, if you construct two buildings very near to each other, they pound each other. For example, each the building is going to vibrate left right. So we know that roughly it is going to be not 4 times h is the code given value. Slightly more also is a possibility. So if the building distance between these two is more than not 4 times h of each building, so then there is a possibility of getting each other touching. So this is another problem if you have multi-story building touching each other. That is why we are having this kind of failure that you can see here. So this is a failure of pounding, and it is a serious issue in real life. So this is also a pounding failure that really happens in the structural system. Uh,